vast area because it could be applied to any mathematical concept when the count or the number of objects are countable. Okay, if I have 10 balls and I can count and I can involve a problem with counting 10 balls, then that could be called a discrete mathematical problem. Okay, as simple as that. But over time, when we do model, that means what? Modeling means what? When we describe a real life situation, that is called modeling. We describe it. So why we describe it? For the purpose of solving that problem, okay, or solving any question rising out of that problem. That's why we use modeling. Okay, and in order to solve many real world problems, we really use many structures. Okay, to make that modeling interactive, to make that modeling simple, okay, comprehensive. That's why there are many structures comes into picture. And these days, because of the ensuing problem areas, we have two structures very famous. They are called tree and graphs. Both are similar in a sense that we studied in the last class, and both are, of course, have different characteristics. Okay. And we have also talked about a problem called recursion, and we try to understand recursion by looking at a queue, and we try to solve a question. So this is called recursion modeling. Okay? And why we do recursion? Just to model a real life situation, and the situation goes like this: when the last person in the queue wants to count the number of persons ahead of him, how does he count? So this question we try to answer using recursion. Okay. Similarly, we try to understand that graph coloring could be a problem which could be described using discrete structures. And we also discussed about various real life situations which could be modeled using discrete modeling. Okay. Like road and rail network. In this case, you can solve the traffic issues. And we know that because of traffic issues, there are so many accidents are happening. So if you minimize the number of accidents, then your traffic design is so good. And that could be achieved by using discrete mathematical modeling, by using the very typical model called graphs. Okay, and those participants, our esteemed teachers who were absent in the last class, for them I would like to repeat one topic, then we'll move further. Okay, why I'm just taking a recap, because our objective is, while we teach students, okay, we either use puzzle or real world problems. Okay, these are the two ways, or real world problems. Okay, so these are the two effective ways, as researchers says. If we present this way by posing puzzles or by relating some real world problems, and we try to solve those problems with the application of mathematics, then we can really catch the imagination of the students, and in a process they will flourish in their daily life. Okay, so we can go by puzzle way or relate the problem with a real world interesting problem. Okay, now let me differentiate what is tree and what is a graph. So of course, these are the discrete models, we can say, or can say discrete structures. Okay, and we know that the similarity between them is that these are the structures with dots, or we can say call it vertex, and edges, or can say lines connecting the dots. Okay, for example, if I have dot like this, we call it a tree. This is an example of a tree. Okay, so of course it satisfies the definition that it has so many dots and it has the lines connecting the dots. And what could be a graph? Tell me. The graph could contain, again, the dots and lines, but it could have, okay, parallel lines, or can say multiple edges, okay. It can have a loop or circuit, both are synonym, okay, loop or circuit, or they can have, my daughter is disturbing. She is showing something. Okay, I got distracted. So let me focus. It could have parallel lines, loop or circuit, or self loops. Okay, so how does they look like? I'm repeating this because I believe in understanding the things clearly rather than covering so many things and so many doubts. So here I can have again the dots. I connect to the lines, okay, and it becomes a loop, and it satisfies the definition of my graph because it may contain a loop, okay, or circuit. What does it mean by parallel line? This dot and this dot has one line already. If I draw one more line to connect them, it's also possible. Okay, and self loop does mean that I started from here again without reaching anywhere, again reach here. So this is called self loop, you know. So a graph can contain all these three things, but a tree cannot contain any of these things, you know. Okay, so a tree cannot be, having such a loop. I cannot connect that. If I connect, it will no longer be a tree. Okay. Similarly, I cannot have parallel edges. It could no longer be a tree. Similarly, I cannot have self loop. It could no longer be called as a tree. Okay. Now I hope you've got the idea about a tree and a graph. Okay. Now we'll try to solve this in looking at some puzzles and looking at some real world problems. Okay. My idea is clear. So again, let me tell you three things. First, we try to focus on popular discrete structures, tree and graph. Second, how to present the students by using puzzle way or by giving some games. Okay, puzzle and games could be pronounced synonymously, both are having similar flavor. Or we can pose a real world problem so that students will get interest in that. Okay, and at this point of time, let me go to the slide to say something, why it is happening and why the researchers are really focusing, and what is the need of studying this. There is a research paper, I cited this research paper yesterday itself, Discrete mathematics in primary and secondary schools in the United States. Because of these reasons, I have colored all these things for objectives. The last objective is that discrete mathematics is the language of a large body of science and underlines decisions that individuals will have to make in all walks of their life, So by infusing the discrete ideas, discrete mathematical ideas into our kids, children, students, high school students, what we achieve is we are really grooming them, okay, to take right decisions, and they must have the problem solving skills, whatever the walk of life they are in, okay, their own lives, in their professions, as citizens, as a social, responsible social member, and so on, okay. And increasingly, discrete mathematics is used decision makers in business and government, and in any application like communication is the need of the day. So it is also rampantly used in telecommunication networks, computing, information transmission, and so on. Okay. Also, it could be used in healthcare problems, in biology, in chemistry, in automated manufacturing, and transportation. So these are the observations the researchers has observed. The researchers has come up with in the research paper. Overall, I can conclude here that this is very much needed for our students in future. That's why you have to introduce this in their school level studies. Earlier, We are not caring about these things, you know. Our traditional teaching process is like to cover the syllabus and to give as much as information to the students. What they lack is the wisdom. What they lack is the problem solving skills. What they lack is how to manage stress, you know, because life is full of problems and we have to manage stress as well. So discrete mathematical models are also used for strategy management, risk management, stress management, and so on. Okay. So this is the kind of flavor, you know, cognitive ability we have to instill in them. So this is one observation. Otherwise, you will not be motivated enough. You think that, okay, what is the big deal of talking about these things? Okay. Now, what to teach? I come across in cspatsala.org. That website has been said to all of you. I hope so. CS Patsala I have not opened yet. Yes, it's there. cspatsala.org. You could see the screen here now. Okay. So from there, I got this information that we can apply the theme of discrete mathematical modeling to even junior school students by recognizing street map, you know, that can be represented by a graph, which is a discrete structure. And we can teach middle school students the roots, okay, the roots to be represented by paths in the graph. And high school students should be able to find cost-effective way of linking sites into a network. We'll talk about all these problems one by one. Okay, so the whole idea is that we have to think of the level of the study and introduce the problem with a degree of difficulty involved. You know? Any doubts so far? कुछ डाउट है आपका? All of you got, yes, all of you got the difference between a tree and a graph. Can we proceed further? Yes, no? Yes or no?
Yes, sir.
Yes. Okay. Yes, good. Somebody has to say me yes. Otherwise, I'll be thinking that all are taking breakfast nap. Some are interested for lunch nap. I do so. But if you have a very heavy breakfast, also you have a pleasant nap. But you should not miss the content. And I'm trying my best to not to make you bored. Okay. Let me introduce one of the slides from CS Patsala, because as per the organizers, our esteemed organizer Sonivar sir, he is also promoting CS Patsala. So we also decided to promote CS Patsala because it has so nice content developed by the esteemed researchers. So let me introduce one. Okay. Now you have the idea about tree and a graph. So here in my slide, on the very first slide, you could see the screen? Oh, it takes so much time. Okay, I'll show you this way. So 3 dots are there, and there is a cycle there, so it cannot be called a tree. So here I have 3 dots connected with 3 lines. It's a graph. Okay. Now, another one. Here I have 5 dots. Okay. I can introduce my students like this. 5 dots and connected lines. Now, question is, can you remove some of the connections or edges of the lines so that there are no loops but no dot is alone? Okay, that's the question. So we have many solutions, you know. You see here is a solution. This is my input graph, okay? And we have to remove the circuit. See, there is a circuit like this. Could you see on the screen? Some of you have to acknowledge Can you see the loop or circuit I have highlighted? Please someone respond. Yes. So this loop is nowhere there, you know. This loop is nowhere there. But this is not as per my question, because I asked a question that let's remove all the circuits. Okay. My question was, let's remove all the circuits, all possible circuits, and no dots should be disconnected. See, this is disconnected dot, so it's not my right answer, but this is my right answer and this is my right answer. Okay. See. And in figure C, it's important that just because the lines are crossing each other does not mean there is a loop. You see, let me draw this for you. So you could see that this line and this line are crossed. It doesn't mean that there is a loop. Okay, you can connect this line. I'll tell you. Instead of this line, you connect this in different way as well, like this. Okay. In this case, this line will be not there. Okay, and you cannot assume that this is a circuit. These are the wire connections. You just drag the wire in a different direction. That's all. So these two are my correct answers. Okay. So why I'm doing so? You can ask a question. I started with some dots, some lines connected together, and in a flow, I'm reaching towards a real world problem. You have to keep in mind, whenever you present something, there should be a purpose. That's how we do teach. You know? And being teachers of the student, the kids, you must have much more experience than the teachers like us who teach the bigger students, So what I'm focusing is just to present a variety of discrete models and how to follow the flow so that the students could be interested. What next? What next? It's a kind of series, Sometimes you watch series in TV, a lot of rings and so on, and even the Hindi serials like what they call Saath Nivana Sathiya, Sometimes you are watching Saath Nivana Sathiya, and when the episode is over, we are really upset. Why not to continue with the rest of the content? We have so much curiosity to know what next. So that kind of thing we have to create, and that's really the art of a teacher. Okay, and we have to groom ourselves to have that kind of flow actually. Okay, so there is a say, because we have to tell the students what is a tree. Such a diagram with no loops are called trees, and even if they do not look like trees in the forest, So look at the sideways, and this looks a little like real tree growing from a single root. This right side figure. Okay. Now there is a new term comes up. There is a recap that a tree must not have no loop, and it has the same number of dots as the original dot, but none of them are alone, and you can find a way from every dot to every other dot. That's called a tree. And the name for such tree is called spanning tree. That means there is no loop. See, you see here. It is a diagram, and from that diagram, I can have many spanning trees. So why we call spanning? Because it's spanning over all the dots. Okay. Why it is called spanning tree? It's a typical version of tree. Okay. As I told you, a tree. There are varieties of tree. A spanning tree, a binary search tree, a B tree, a heap tree, okay, a B plus tree, and red black tree, 2, 3, 4 tree, and there are varieties of trees. Okay, I'm not telling those all varieties, just I'm naming them just to make sure that you must know that it's not the end of the world. There are many varieties of trees. And whenever we talk about one tree, let's relate it to a real world problem. So we come across a typical tree here, which is called spanning tree, and we, I mean, we call it like span all the dots. That's why called spanning tree. All the dots are covered, and there is no loop. There is no multiple edges. There is no self loop. So of course it satisfies the tree definition, and it's called spanning tree because all the dots are covered. And can I call this as a spanning tree? Let me ask a question. Can I call? Let me ask a question because you must clarify yourself. Can I call it a spanning tree? Yes or no? Somebody should acknowledge, please. Let me go across to the participants. Is there any question?
No questions.
Okay. Now, the idea is that these right side figures are byproduct of my left side figure. The left side figure is a typical graph, and the right side figures are called spanning tree. Okay. Now we can have a puzzle 2 also. Here is a diagram. Draw any spanning tree out of this. So given a graph, we can have many possible spanning trees. That's the conclusion. Okay. You can have many possible spanning trees. Okay. See, here is a figure, and there are 2 spanning trees given. Now let's relate it. You are in charge of building roads between 5 cities. Here is a very simple map given to you. 5 cities: New Delhi, Pune, Kochi, Chennai, and Ranchi. Okay? And you have to connect these cities such that you can go from any city to any other city. If there will be no road in between one city will be missed out. So we have to make sure that we have to connect all the cities in such a way that we can start from one city and can reach, we can cover all the cities. So you decide to build road from every city to every other city. It's a perfect solution, isn't it? See, this way I can do my job. Okay. If I go to this, this figure, let me draw something. I can connect from here to here. I can connect. I can connect. I can connect. I can connect. Okay. Similarly, I can connect to here, here to here. That does mean that I started from here. Let me present some other way. See, if I start from Delhi, I can go to Pune, and I can have a road to Ranchi. I can go to Kochi. I too have a road to Chennai. Okay, so each city connected to rest of other cities. Now from here, I can connect this to this, then this to this, then this to this. So I make sure that Ranchi is connected to all other cities. Then I can make another attempt to connect Pune to all the cities. Whether it is connected to all of them, no. So I can connect here, then I connect to that, and now it is connected to all. So if I do so by using a very simple logic, then I will end up with what? 10 roads. Now question is, building road cost a lot of money. We cannot afford a perfect solution. We cannot perfect a perfect solution. Means perfect solution is all are connected to each other. But we need something which is cost effective, less cost involved. So the question remains that can we connect them with few number of roads instead of 10? Okay. Yes. And that's the thing called spanning trees can help us find a small number of roads that do not have any unnecessary loops, that connect all the cities, do not leave any city out alone. So we need only 4 connections instead of 10. Get that point? So this is one example of a spanning tree. So it is a byproduct of a perfect solution. And you know the perfect solution that is presented in this slide is very, very costly because it involves 10 roads. And I have a very cost-effective solution which have only 4 roads and none of the cities are left out. Clear? Any doubts? If you have any query, please ask. No doubts?
No, sir.
Yes. Let me- So we can make some observations here. Trees are diagrams with dots and connections but without loops. A spanning tree is a typical tree based on small version of diagrams with loops, which connects all dots but do not have any loops. Okay. One application of spanning tree is designing minimum number of roads that connect cities but without spending too much money. Okay, that's called spanning trees application. Now let me introduce one more flavor of spanning tree. Okay, this is how we proceed. Okay, this is the recap that we have a graph like this structure, and we can have spanning trees like this. Okay. Again, I redefine spanning tree is a tree where no dot is left out. So that if every dot is considered as a city, I can visit all the cities covering the roads. Okay. Now, if there is a question that did you get this correct? Suppose I have this slide there. This is a graph, and I'm trying to create a spanning tree from this graph, and it's called wrong because there is a city which is left out. It is not connected to even a single road. Okay, that's why it's wrong. And it is correct because all the dots span over. This is correct. And this is incorrect because there is a loop involved, and loops are not allowed in spanning tree or any tree. See, here is a loop. Here is a loop. Because of loop, this is not a spanning tree. Okay, I hope you got it clear. And again, I'm telling you, any point of time, if you have any doubt, raise a question, please. And I'll be taking a 10 minutes, 10 seconds gap whenever I'll be waiting for a question. So last time we saw that instead of 10 roads, we can connect all the 5 cities with 4 roads. 5 cities, 4 roads. That's the efficient way of connecting all the cities. Okay. Now there is a different flavor, but all the flavor it says advanced spanning tree we'll be talking about. That means looking at the spanning tree with a different perspective. okay, with a different idea. What is that idea? What it is different? How it is different from my previous example? It says all roads are not the same. You know, some roads are longer, some are shorter, and shorter roads are cheaper to build. You know, get the point. See how you could introduce the students one by one, just like a TV serial. Of course, we can connect all the roads. I mean, all the cities with 4 roads instead of 10. But the idea is whether all those 4 roads are efficient one, because altogether I have to find the minimum distance to be covered when I reach a city, or not minimum distance. I should not say like this. Minimum amount of cost. You know, if the road is shorter, of course, to build the road we incur less cost. So while using spanning trees to connect cities, can we pick can we pick up those roads that are cheaper to build? Okay, to do that we need the distances between cities. So using an algorithm for making spanning trees, we can make a cheapest spanning tree. Okay. And what is algorithm? You have been studied in some classes, I hope so. Okay. I'm also a teacher of algorithm. I'm fond of teaching algorithm. Okay. But in this webinar, my mandate is not to teach algorithm, but to introduce you the typical discrete models. So by using algorithm, we can find a cheapest spanning tree, so that the cost incurred is very, very less. So if I look at a road, you see here is a road which cost is 15, 10, 10, 5, total is 40. Now question is, can we minimize the cost further? Yes, there are many further solutions. You know, for example, here is a diagram of some spanning trees made from the cities connected. You see, I have 5 cities and few roads, and in option 1 my cost is 10. In option 2 my cost is 12. In option 3 my cost is 60. Of course I will prefer a lesser one. Okay, the lesser one is here, which involves cost 12. So it's a typical spanning tree, and in other words, to build lesser cost roads, which involves less distances, we need to look at the spanning tree with a different perspective, that is called a minimum spanning tree. That means that given a graph like this, which connects all possible cities, if I find the byproduct, that's called spanning tree, and I can have many, many spanning trees possible, and I have to explore the spanning tree, which has less cost. Okay, this is called a very typical nice example. Any doubts you have? No doubts? So the idea is we revise spanning trees, and finding spanning tree. What is the advanced feature we study now? Finding spanning trees based on their cost. Okay. So we studied 2 perspectives of spanning tree. One is, can we connect all the cities without letting one? That is one application. Now the second one is that whenever we build the roads, can we spend much less cost? Another application. Okay. I hope you understood well. Any doubt? Please ask questions. Do not hesitate, you know. And when you ask questions, really it makes very productive. We have enough time. We have still 40 minutes to go. Okay. Let me introduce one more model. Graph coloring. You can introduce the map to the students, and you can ask the students that how can we color the map. Why coloring map is essential? Because you cannot map the whole India with the same color. In that case, we cannot identify the boundary of one state from the another. That's the theme behind color mapping. So initially we'll ask that, okay, let's color. Now the next question will be, how many colors you have used to color India? Somebody says 10, somebody says 8, somebody says 9. Then the next job with the students is, can you minimize the number of colors you have used? Okay, with that flavor we can proceed. We map, we colored the state with orange, then we mapped with some kind of blue, then purple being used. So three colors being used. It is said that we require maximum 4 colors to color the map of India. Okay, you check out by yourself. Okay, there is a very popular theorem that this is called 4-color theorem. Any map could be colored with 4 colors. Okay, but sometimes we need 5 colors as well. I will show you. Here is an America. So that's how we can proceed one by one. See, I'm saying that 5 colors also needed. Let's see. Let's look at this figure. We tried with red. We tried with some different colors. We tried with some different colors. Okay, that's an example. Now look at here. Is it possible? Is it only applicable to maps? Let us color this arbitrary picture and see for ourselves. 5 colors. The fifth is the surrounding color red. You know, because if there is a rectangle and inside the rectangle there are many shapes, and to demarcate the boundary between the shapes we have different colors, but again the left out part could be colored white or red. So instead of white I used red. I should have left it white also. White is also a color. So as a whole I need 5 color to make these shapes differentiated between each other. Okay, so now the idea is we can convert this we can convert this graph coloring problem to map coloring problem to a graph coloring problem. Okay, so why I do so? Because of 2 reasons. Reason 1 is how I can my pen is not working. Yeah, this is reason 1. And this is reason 2 why I talk about graph coloring. One is the map coloring problem could be considered as a graph coloring problem. And for that matter, any real world problem can be visualized as a graph coloring problem. I'll show you one more graph color problem, very interesting problem after this. Okay. So any problem could be applicable if it is possible. You have to think of that as a graph coloring problem. Then what is the minimum number of colors required is also another exercise. So with these 2 exercises, you can teach our students another application of discrete model called graphs. Okay. So this is a very simple graph. Now I'll introduce you another typical graph called bipartite graph. Okay. See. It is a very different graph. It has 2 colors. You look at the graph, it is only 2 colors, blue and red. The vertices are called blue and red. Okay. And before that, I have really in a hurry, I've skipped something. Before that, going to that one, let me tell you that graph coloring could be done like this. What are the steps you're taking? Color these. See, this is a graph, and you can color this. See, the neighbor nodes should not have the same color. Neighboring nodes should not have the same color. Okay, that's why here I have different colors, and 2 neighboring nodes have 2 different colors. Now the idea is this is a node. I cannot use blue. Okay, I cannot use this color. I cannot use this color because that will be adjacent. So I can use some different color for this. Okay, that's how the graph problem could be visualized. I can use a different color. Okay. So vertices with connection have different colors. In other words, two neighbor nodes cannot have the same color. That's how my map is all about. Two neighboring regions cannot have the same color. So what you say is that your map could be represented as a graph, and you can solve the problem. Okay. And let us do a bigger complicated graph. You can give such kind of complicated problems to your students, and the complications should be increased in incremental way. It's not like all of a sudden you give them a very complicated problem, but you have to start with the easy one, then a bit difficult one, then you can move to a very complicated one, and so on. So we have learned that graphs can be used to minimize the number of colors in maps. So what is the use of this coloring, map coloring in our lives? Where else you can use this? You have to reply this question to students. And at that moment, another application comes to our mind that we can apply this for school timetable. And we learn all this in the next class. It is saying, but I didn't find the school timetable explanation in CS Pathshala. But you can come up with this as an exercise. Okay, how the timetable could be related to graph coloring. Our timetable problem is very much complicated, you know. We should not have overlap classes for the same group of students. And for a teacher also, we cannot assign two subjects in the same time slot for the teacher. Okay, so these are the complications, and we can apply graph theory or discrete mathematical modeling to resolve those issues. Okay. Now let me tell you the new problem at hand. That is another application of graph, a typical graph called bipartite graph. So this graph has only two colors, you know, not more than two. So what kind of problem we are dealing with? You can visualize this graph, you know. In other words, it is a graph whose vertices can be divided into two independent sets. I can visualize it as two parts. Let me put this in perspective. See, only two colors. This is color one, color one, color one. This is color two, and color two. And two colors. Now, let me name those nodes A, B, C, D. You know, I have two different sets. A is colored blue, C is colored blue, E is colored blue. And B is colored red, D is colored red, F is colored red. So a bipartite graph is a graph who has two independent set of dots or nodes. We can call A, B, C, D, F as nodes or dots or vertex, you know, these are synonyms. And the lines could be called as lines or edges or connections. And I call them as two independent sets. Okay, that means I can have the node for A, B, C, D, E, F, and A is connected to what? Tell me. A is connected to B, and A is connected to Let me use some different color just for design or to make differentiate the things. See, A is connected to B and A is connected to F, you know. B is connected to C and B is connected to A already. Now C is connected to B and D. D is connected to C and E. And E is connected to F and A. Sorry, E is connected to F and D. Okay, here I have 6 edges. I just mapped this. I want to visualize this figure 1 and figure 2 are equivalent, you know. And it's a 2-color problem. So whenever a graph is 2-colored, it's a bipartite graph, and it could be visualized either this way, visualized this way, or this way. Okay, and what is make it special is there is no connection between A, C, and E. That's why it's called an independent set. You know, see there is no connection between A, C, and E. Could you see? A, C, and E are not connected. You see, A, C, E. Look at here, this node, and this node. They have no connections. That's the beauty of bipartite graph. And you can make use of this for a real world problem you solve by yourself for timetable problems, as I told you, student and classes. So we might create a graph that maps every student to the classes they are taking. Such a graph can be used to determine conflicts, that is when classes cannot be scheduled together. Okay, so bipartite graph would be very much applicable to schedule the classes, in other words, timetable. Any doubts? Do you have a note? I'll take a 5-second break just to have some water. Not 5 seconds break, a 10-second break. Sunivar sir,
Okay, sir.
10 seconds break.
Let's take some time break.
Uh-huh. Hello, I'm back now. Am I audible?
Yes, sir. Audible.
Yes, yes. The participants also must acknowledge. Alok sir is responding. I must make sure that some of the participants must acknowledge whether I am audible. Whether I am audible.
Yes, sir. Yes,
Yes,
sir.
sir, you are audible, sir.
Yes, yes. Very good. That's nice that you are attentive. Okay, let's back to the discussion point. Uh, let me tell you before I proceed. Let me tell you how many of you are enjoying. Raise your hand. If you're not getting bored, enjoying really, raise your hand. If you're getting bored, do not raise your hand. Okay, many participants are raising their hands. Yeah. Okay. Okay, that's good. Only three. Okay, many. Six. Okay, that's great. Now, as I told you in some slide, in some of my explanation, that either we can teach the students by relating some real world problem to our discrete models, or puzzles or games. Okay, let me tell you one game I've taken here. If I'm not, my screen is visible to all of you. So the game says that sitting problem. 9 members of a new club meet each day for lunch at a round table. They decide to sit such that every member has different neighbors at each lunch. So how many days can this arrangement last? Okay, simple. 9 members we have, they will be sit together for lunch in a round table, and we have to have different arrangements. So how uniquely we can different? Every day it's a unique arrangement. So of course, in how many days all my unique arrangements will be over? That's the thing. You look at here. So 1, 2, 3, 4, 5, 6, 7, 8, 9 people are there. So of course 1, 2, 3, 4, 5 is one solution. Okay. See, one solution is simple as that. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 1. This is the round table. Simply like this. And any other arrangement is possible. Any other arrangement? Look at the diagram. Why this diagram is required? See, it's a complicated problem, and to make this problem simpler, we have applied graph. Simple. Okay, because see, whenever appearing even aptitude questions in many exams, they really check the aptitude just because how far you could digest that problem for coming up with the answer. Digest that problem does mean that you have to visualize this problem in a simple way. Then only you can get the solution. So simplest way of visualizing a complicated problem is here, one graph. Okay. And another solution is like this. We have to start from 1, then the next person to 1 will be 3, then the next person to 3 is 4 or 5. Then you tell me, then 2, then after 2 it is connected to what? 7. Then from 7 it is connected to 4. Then next to 4 my 9 should sit. From next to 9 who will sit? 6. Next to 6, 8 will be sitting there, and 1 will be sitting there. So I have first day unique arrangement, and second day I have another unique arrangement. Any more possible? Tell me. Here is another answer. Answers are given here. Okay. 1, 5, 7. You see 1, then 5. See, I can connect 1, 5. See, after 1, 5, I can connect to 7. Okay, 7 to 3. Means the idea is I have to not think much, but to connect the dots. How simple it is. See, it's a very complicated problem, man, I'm telling you. But the idea is by putting a graph, I have 4 solutions. If first though I saw you the very first solution, simple 1, 2, 3, 4, 5, 6, 7, 8, 9. Then I connected the dots. Then I'm connecting the other possible options like 1 and 5 was not connected. Once I'm 5, I can connect to 7. Then after 7, I can connect to 3. After 3, I can connect to 9. After 9, I can connect to 2. Then after connecting 2, what is my straight number? You tell me 2 could be connected to 8. And 8 could be connected to 4. 4 could be connected to 6. And 6 can be connected to 1. This is one solution. Getting a point. Still in the graph, there is, I got so far 3 unique solutions, 3 unique arrangements. Fourth arrangement is there. Let me tell you. Let me know from you. Let me know from you, and let me erase this so that you cannot see. Let me discolor this so you cannot see the answer. But I am able to discolor. Yeah, discolor. Because teachers really hide the answer from the students, isn't it? So as part of the webinar, I'm also hiding the answer. So can you tell me the next 4th unique solution? It is there in the figure. Tell me, let's interact. Let me go across to some of the participants. You try, please. I'll be waiting for you for 10 seconds. Let me wait for at least one of you could answer. I hope so. See, there are still the lines could be drawn. Are you trying? Can you, some of you acknowledge who are trying? Please respond. None of you are trying, it seems. It's a very typical problem, and this problem could be introduced to from class 6 onwards. It's not that difficult. For 6, 7 class student can understand this. At most, you can introduce to class 8. So why I'm telling this? Because I told you that we can have puzzles like this, or we can have real world problems of many kind. That's why I'm introducing you this problem. See, if you are not coming up with the answer, I'll show you the answer. 179, you see that I'll color them. Let me use a different color. See, 1 and 7 is not connected, you see. Still one new answer to be explored. 179 is not connected, you see. 79 is not connected yet. So giving us a hope that it is a new solution now. 9 to 5 is not connected. Five to 8 is not connected yet. 8 to 3 is not connected yet.
सर 1 to 4 भी तो बना सकते हैं, 1 से 4 वाला.
हाँ, 1 से 4 वाला आएगा रास्ता बाद में. अब आप किसी भी तरीके में जा सकते हैं, नो डाउट. एंड 8 to 3 गए. ओके, मैं 1 से शुरू किया, तो अब 1 to 4 होके भी जा सकते थे. ठीक है, उस केस में आपको ये वाला आंसर मिलता, लेकिन कनेक्शन तो वही होता, आपको ये रिवर्स ऑर्डर में मिलता. ठीक है, 1 4 2 4 करके मैं 1 to 7 कर दिया तो मुझे यही मिला, लेकिन ये सीक्वेंस यही होता आपको. ठीक है, वेरी गुड क्वेश्चन. समझ रहे हैं ना? So where I was 8 to 3, then 3 to 6, 6 to 2, 2 to 4, and 4 to 1. Clear? And as some participant is saying, so let me try this. Whether if I start from 1, instead of 1 to 7, I'll go from 1 to 4 and let me see the answer. If I'm going from 1 to 7, this way I'm going and I'm getting the answer. If I go to 1 to 4, then how could I see the answer? Let's see. Possible, why not? Okay. Yeah, 1 to 4, then 4 to 2, or 4 to 8 also can go. At this point of time, we can ask a question whether 4 to 8 is possible or not. But I'll tell you, there was some situation whether 8 to 4 was there. Okay, that's why it is wise enough. It's wise enough not to erase the lines, you know. Okay, after I connect 1 to 3, first solution, second, third, just because it was so clumsy, I erased that one. Otherwise, I should have the options like this: 1 to 4. Then at this point of time, I can get the answer for 2. Okay, then 2 to 6, then 6 to 3, and so on. So this reverse order we can get. So this way I can have 4 unique solutions. So how many unique solutions there? There is a theorem for that. This is a very high level mathematics, but it has been proved that if n is odd, I can have n minus 1 by 2 number of solutions. I mean possible arrangements. If n is even, I can have n minus 2 divided by 2 number of possible arrangements. Just because in this example, we have n equal to 9. 9 is odd. So 9 minus 1 divided by 2 is 4. And accordingly, you get 4 unique arrangements, as you saw. Okay. Should I proceed further if you do not have any doubts? Yes. Now we have 10 more minutes to go. I should not take much time and disturb your lunch break. Let me quickly introduce 2-3 more concepts, which could be utilized as the concepts to introduce in your class and relate to real world problems. One is called Euler Path. Okay. And one is called Hamiltonian Path. So a path that uses every vertex in a graph exactly once is called a Hamiltonian path. An Euler path is a path that uses every edge of a graph exactly once. Okay. If I ask you, given a graph like this, whether this graph has a Euler path, whether this graph contains a Hamiltonian path. A path is something where we start from one place and reach to another place. Euler path means you have a path that has every vertex in a graph exactly once. So हम जा सकते हैं यहाँ से यहाँ exactly once, यहाँ से यहाँ, यहाँ से यहाँ, यहाँ से यहाँ, यहाँ से, है ना? तो इसमें यूलर पाथ है. And Euler path, and Euler path is every edge of a graph is exactly twice. Okay. Exactly here once. Whether it has Hamiltonian path, in that case, vertex should be. Okay, I visited this, I visited this, I visited this, I visited this, I visited this. So this is simple graph which is both Euler and Hamiltonian path, which has both Euler path and Hamiltonian path. And you can introduce this to students for various kind of problems. Okay, so there is a typical problem called traveling salesman problem. Which is a typical problem involving with Hamiltonian path. Though it seems like traveling salesman problem, it has so many real world applications in computer networks, in computer circuit design, and in brain network analysis and so on. What does it say? We have a complete graph like this. Again, a new terminology comes into picture, complete graph. And each graph is a city. And a travelsman, salesman, who wants to travel. Okay. Each city exactly once. Okay. Each city is what? Vertex. So of course it suits to the Hamiltonian path example. Every vertex exactly once. Even if we can repeat the edges, that means here we can repeat the edges. You can repeat the edges, but you cannot repeat the vertices. That's not permissible. So you can visit all the city with minimum cost involved. And every road has a cost, you know that. And depending upon the distance or depending upon the terrain, we have a cost involved. If from city 1 to city 2, I involve a cost 4 rupees, city 2, 9, or this may be 10, this may be 3, this may be 5, this may be 6, and so on. So I have many options possible. Okay, but I have to find such an Hamiltonian path so that the cost involved is very less. Okay. This could be a problem given to the students. And we have different purposes for Euler path and Hamiltonian path. And as a teacher, we have to try to relate these to real world problems. This is one example. Another example I would like to give is vertex cover. Read out while I'm doing to access my pen. You just read out a vertex cover of a graph is a set of vertices that includes at least one endpoint of every edge of the graph. Okay, see how we can come across different terminologies and how can make use of them, those things as a discrete mathematical model to describe a real life situation. Okay, tell me what kind of real life situation we can relate this to. What it says, a vertex cover is a set of vertices that includes at least one endpoint of every edge of the graph. And it has a minimum problem also, just like spanning tree. We defined spanning tree, talked about an application, and we also redefined the spanning tree and talked about another application that is called minimum spanning tree. Similarly, it's a vertex cover, and we can have a minimum vertex cover also. So given a graph like this, suppose, this is the graph, A, B, C, D. Okay. What is vertex cover? A set of vertices that includes at least one endpoint of every edge. So मैं एक edge को process करूँगा. Okay. Let's consider this edge. and randomly you can pick either B or A. Possible? So a vertex cover of a graph is set of vertices that includes at least one endpoint of every edge of the graph. Okay. Suppose I wanted to take A. So this edge is covered. Suppose I wanted to take A. So this edge is covered. Cut down. Consider this. A is already there, so I need not take B. Consider this. A is covered, so I need not consider C. So all these edges are over. Consider this edge. Okay. So far in my vertex cover, A is the only option there, and for this I need to have at least one endpoint to be part of my vertex cover. So I randomly choose D. So this is also cover. Cover means what? I have to choose the vertices in such a way that all the edges will be covered. Okay. Now what is the left one? BC. In BC, I have to choose either of one. Okay, I suppose I choose B. You can choose C also. So this also covered. So what we conclude that there is an example that A, B, and D is the vertex set which is known as vertex cover, because out of these four vertices, these three are enough to connect all the edges. You see, these two are enough. See, not all the edges, but set of vertices that includes at least one endpoint of every edge of the graph. It's not like spanning tree so that I can cover all the edges, all the vertices, and it's not like a Euler path so that I have to cover all the edges. It's a vertex cover, just to make sure that all the endpoints are covered. Endpoints. So how many edges are there? You tell me. This endpoint is covered. Its endpoint is covered. B. Its endpoint is covered. That is D. Its endpoint is covered. Both A and D are there. And in this line also endpoint is covered. So to what kind of real world problem I relate this to? Okay. If you think of this problem, you can relate this to deploy the minimum number of traffic personnel in your crossroads. Okay. So whenever you use minimum.
नेटवर्किंग में सर
हाँ, नेटवर्किंग में minimum number of routers you need.
जैसे नेटवर्किंग में हम लोग करते हैं ना ब्रॉडबैंड सर्विसेज.
हाँ, but networking तो for the kids you cannot introduce though, but you can introduce the traffic problem to kids and discuss vertex cover and discuss minimum vertex cover and try to realize that crossroads, and if I find minimum number of vertices so that all the all the endpoints are covered, so that makes sure that we can have that many number of traffic persons sufficient enough to handle the traffic. That's a very good example to teach higher students that networking. Okay, so these are the examples of real world problems, and there are many others also there, but due to time constraint, I hope I already covered 1.5 hours, and I should not go beyond that. But before I conclude, let me finish one more example. See, I can have a discrete structure like this. Okay. So this is a substation, and these are the villages from substation we are supplying power to. Okay, so it is a kind of discrete structure, and if the power goes here, goes off, or there is some kind of problem happen to this power station. Okay, all my villages are getting disconnected from electricity. Got the point? So you can ask a question here that how many substations I need to connect to these villages. Get a point? So we call it a topology. So topology is how you can connect different dots to deliver a supply. The supply could be electricity. Okay, the supply could be a gas pipeline, and the supply could be digital network, or you can say your broadband network, and so on. So you can introduce the network reliability, but you cannot use the word network reliability to the students. They do not understand. But you can tell them कि okay, यहाँ current चला गया, तो बाकी सारी जगह में अंधेर हो गया. So how many at least substations I need? In what way I can reorganize my substations so that even if one goes out of power, all four will be getting disconnected and getting connected. और अगर एक ही में जाता है तो minimum number of villages to be affected. Because substation हर जगह तो कर देंगे भी तो cost effective तो नहीं होगा ना. तो प्रॉब्लम तो हर substation को आएगा जरूरी नहीं है. इसीलिए हमें दोनों चीज देखना है. Number of substations also need to be minimized. At the same point of time, we have to ensure reliability so that at any point of time, most of the villages are not getting affected. Okay, that could also be a kind of discrete mathematical modeling to describe the real life situation where you can introduce some kind of service-oriented network topology. Topology means the network structure. Network is nothing but a graph here, okay? And you can have trees, self loops, multiple edges possible. I will not say topology could be a tree, okay? So it could be a graph and so on. So this is how we visualize and interpret different discrete models and their definition so that we can introduce the kids in relation to many of real life situations. With this, I wrap up my discussions today. And if you have any more questions, please go ahead with the queries. Do you have any queries? There are only 12 participants there. Please go ahead with questions. Do not hesitate. Okay, I hope you do not have any queries with you. And if any point of time you have many queries to be asked, then you can collect the email ID from the organizers, or let me give my email ID here itself so that you can contact me at any point of time. In the chat box, I'm just typing my email ID so that everyone could see. Okay. And as a teacher, you can digest many books. Also, the prescribed books could be computer applications. I mean, graph theory with application to computer science by Narasimha Dev is a very good book. And another good book is called Douglas B. West, D.B. West Graph Theory by Douglas B. West. These two books could be referred to know many technical terminologies. Then you can come up with many problems and puzzles, games, and so on. So with this, I conclude, and thank you so much for your patience hearing. And let me request organizers, either Alok sir or Shanivar sir is there to brief you before you go for lunch. Or Jayanta sir is there, hopefully. No, maybe network problem there. Okay, with this, I would say thank you so much, and I'm disconnecting the call now.
Thank you, sir.
Welcome.
Thank you, sir. Thank you.
Thank you, Bhatta sir.
Welcome. Welcome.
Hello.
Hello. Moment,
Hello.
Mr. Sir. Hi, sir. Thank you so much. Thank you.
Hello, Bhatta sir. Can you hear me?
Yes, sir. Please go ahead, Mr. Sir.